Section 6 for the logistic equation. The second example here, second video, we're going to solve and analyze logistic differential equations. Continue on with that. I'm Mr. Antonucci, and here's example 3. We want to verify graphically, numerically, and algebraically that the upper limit or the carrying capacity of this equation is 4. So the first thing that we're going to do is hop over to Desmos and graph this. So here we have our graph of f of t. I've entered it as a function of t, and the reason for that is because this is analyzing it graphically. And if I graph y equals 4 on here, let me just change the color. And you could see that the carrying capacity is 4, which is the L, the numerator, the 4 in the numerator here. If I draw the line y equals 4, you could see that that's a horizontal asymptote to this graph. And if you pick any point and zoom really closely in, you can see that it keeps getting closer and closer and closer. So the next thing we want to do, so that's verifying it graphically. We want to do it numerically, which would be with a table of values. So you could set up a table here. Instead of x1, we're going to call it t1, and instead of y1, we're going to call it f of t1. So if we just start at 0, you could see the point comes on here, and plug in 1, 2, 3, and so forth. We could see that as let t move to the right, we could see the y values approach 4. Now, once you get past 6, notice the y value is 4, but not really. We've just exceeded the number of decimal places that Desmos rounds to, and so it rounds it to exactly 4. But it's actually like 3.999999999 and so forth and so on. It never actually hits 4. It just adds more nines to the decimal. The last way we want to verify this is algebraically, and that's where you have to literally show your work for the limit as t approaches infinity of 4 over 1 plus 2e to the negative 3t. If we isolate, if we just look at the e to the negative 3t, remember that's e 1 over e to the 3t because of the negative exponent. If I take the limit as t approaches infinity in this case, this denominator is going to get increasingly large, essentially 1 over infinity, which approaches 0. So this right here, this term, is going to approach 0. And 2 times 0 is 0. So the limit as t approaches infinity is really 4 over 1, or just 4 in this case. So that's verifying it graphically, numerically, and algebraically to find that the carrying capacity is 4. The next thing we want to look at is determine the point of inflection for this graph. So in a previous example, we already found the first derivative, and we found out that it was 3y times 1 minus y over 4. This is a logistic function. We also know that its derivative follows the logistic differential equation form. The next thing we can do is find y double prime in terms of y and y prime. So we would use the product rule, the derivative of the first times the derivative of the second, which would be negative y prime over 4, plus the second times the derivative of the first, which is 3y prime. Simplifying that a little bit, we can factor out a 3y prime, and you'd be left with 1 minus y over 2 if you did that. Now this is helpful because when y is between 4 and 2, then the second derivative is less than 0. Similarly, when y is between 0 and 2, the second derivative is going to be positive. So the graph is concave upward from 0 to 2, concave downward from 2 to 4, meaning y equals 2 is our point of inflection. Now, if we plug y equals 2 into the original function, we would have 1/3 natural log of 2, comma 2 would be our point of inflection for this graph. And we'll bring that up in Desmos to show you that. Here we have our graph of f of t, I call it f of x here, and I highlighted the inflection point right here. Notice before this point, the graph's concave up. After that point, the graph's concave down. If I graph the second derivative in blue here, you could see that when the blue graph changes from positive to negative, that corresponds to where the purple graph, the original function, changed from concave up to concave down. This point right here doesn't really have significance for what we're talking about at this point. It's just the intersection point of the first or the second derivative and the original function. So there we go. We found the point of inflection. One interesting property is that the point of inflection occurs at half. Here's the point here, at half of the carrying capacity. See how the y value is 2 and the carrying capacity is 4? That's always going to be the case with the logistic growth curve, is that the point of inflection is always going to occur at the t value that gets you half the carrying capacity. So remember, you basically would just solve the equation for when y equals half of L. So that's it for this one, guys. In the next one, we're going to talk about some applications for the logistic growth curve.